Have you ever wondered about the existence of things that pop up and vanish out of nothing in our universe? How are you doing? Well, it might seem counterintuitive to anyone, but it's true, and it's a phenomenon called quantum fluctuations. Whoa! To understand what these are, think of Heisenberg's uncertainty principle, which tells you that for certain pairs of physical properties, you will never be able to get null uncertainty on their measurement, and that the more you know about one of them, the less you know about the other one. Take for instance a photon passing through a measurement device. The more certain you are of its energy, the less precision you will get about the time at which it arrived, and vice versa. Astounding, but what if we apply this to the vacuum? Well, it first won't have null uncertainty on its energy, and it turns out that this energy is used to create a new kind of particles called virtual particles. But wouldn't we be cheating nature, namely the law of conservation of energy? The explanation for this is that these particles are created in pairs, and they'll soon return the energy when they collide and disappear. These are similar to classical particles, but with less mass and invisible to us. Then how do we? But we can actually see their effects. And that's just what Henry Casimir predicted in the 1940s. Imagine two isolated metal plates separated a few nanometers apart. These would move towards each other, but not on account of any force of traction, but instead a push generated by virtual particles. And this happens because of the wave-particle duality, as there is a constraint on the wavelengths of the particles created within the plates, being most of them created out of the plates, which in turn will exert a tiny resultant pressure on it. Okay, I guess that's enough. But what is up there? If we have an accelerating plate moving at relativistic speeds like 5% of the speed of light, backwards and forwards, it will allow some pairs to be created such that one of them loses its twin behind the plate, taking energy from the plate to transmute into classical particles. And it just so happens that in the universe, this also transpires nearby the event horizon of a black hole, where not even light can escape, allowing some virtual photons to transmute into classical photons, which is known as Hawking radiation, named after Stephen Hawking. But in this case, the energy is taken from the mass of a black hole, being its effect insignificant compared to the absorbed mass of other cosmic bodies. And why do physicists care? Well, this constitutes the basis of one of physics branches called quantum field theory, which is currently its most comprehensive theory and employs virtual particles as the medium for quantum interactions as expressed in the Feynman diagrams in a similar way to the electromagnetic field. And this is only the beginning.